Welcome back. We have 5 derivative rules already in the toolbox: the power rule, the sum rule, the constant multiple rule, the product rule, and the quotient rule. They handle polynomials, ratios of polynomials, and products of any functions you know how to differentiate individually. There is one thing they cannot touch: compositions, sine of x squared, e to the 3x, the quantity 3x plus 1 raised to the 5th power. Each of these is one function feeding its output into another function. None of our 5 rules will move it. The chain rule does. It is the third and biggest derivative rule, and it accounts for more of real-world calculus than the other 5 put together, because real functions in physics, engineering, statistics, and machine learning are almost always nested. Today we prove the chain rule, give it the cleanest physical intuition I know, see why Leibniz's notation makes it look almost trivial, work 3 examples, chain 3 levels deep on one of them, and use it to glimpse the full power rule for any real exponent. Let's go. Before we state the rule, let's see why we need it. Consider h of x equals the quantity 3x plus 1 raised to the 5th power. Try to differentiate this with what we already have. The power rule, as stated last episode, applies to x to the 5th, not to anything to the 5th. So we can't read the derivative straight off. The product rule could be made to work in principle: write the function as 3x plus 1 times itself 5 times. Then apply the product rule 4 times. It works. It is also miserable, and it scales horribly. We could also expand the binomial first to get a degree 5 polynomial and differentiate term by term. That works here because the inside is a polynomial. But the moment the inner function is sine x or e to the x or square root of x, expanding is no longer an option. There's nothing to expand. We need a rule that peels the outside off the inside without ever expanding. That rule is the chain rule. Here it is. If g is differentiable at x and f is differentiable at g of x, then the composition f of g is differentiable at x, and its derivative equals f prime, evaluated at g of x times g prime of x. Read that twice. The output is a product of 2 pieces. The first piece is f prime, the derivative of the outer function, evaluated not at x but at g of x, the value the inner function produced. The second piece is g prime of x, the derivative of the inner function evaluated normally at x. In Leibniz notation, with y a function of u and u a function of x, the chain rule reads the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x. Visually, the du in the numerator of one fraction and the du in the denominator of the other look like they cancel, and that visual cancellation is one of the most beautiful pieces of notation in mathematics. It's also why Leibniz's denotation crushed Newton's dot notation in the historical record. We'll come back to that. In plain words, differentiate the outside, leave the inside alone, then multiply by the derivative of the inside. The cleanest physical picture of the chain rule: a hiker walks up a mountain. The hiker's elevation is a function of time, call it h of t, measured in meters per second of climbing. The temperature at the mountain depends on elevation, call that t of h, measured in degrees Celsius lost per meter of climb. The hiker doesn't directly experience elevation, the hiker experiences temperature. So the composition is what matters, t of h of tt, how the temperature changes as a function of time. How fast is the temperature dropping per second? 2 rates combine. The hiker is gaining h prime of t meters per second, the mountain is losing t prime of h degrees per meter. Multiply the rates. Meters per second times degrees per meter, the meters cancel, the seconds remain in the denominator, and you're left with degrees per second. The dimensional analysis forces the answer. The chain rule is rate of outer times rate of inner, because that's how nested rates compose, with units that cancel exactly the way fractions do. Every chain rule application is some version of this hiker. Here's the picture. The input x enters the first function box, g. The function g processes x and produces an intermediate value u, that's g of x. The value u then enters the second function box, f. The function f processes u and produces the final output y, that's f of u. 2 boxes, 1 input, 1 output, with an intermediate variable wedged between them. Now ask, how does I respond to a small change in x? The change has to pass through both boxes. A nudge in x produces a nudge in u, scaled by g prime of x, that's the rate of the inner box. The nudge in u then produces a nudge in y, scaled by f prime of u, the rate of the outer box. The total scale factor from x to y is the product of the 2. The derivative of y with respect to x equals f prime of u times g prime of x, where u itself equals g of x. The box and arrow diagram is the chain rule made visible. Every chain rule calculation is a walk through this diagram, multiplying the rate at each box you pass through. Now the proof. Let u equal g of x and y equal f of u, so y is the composition. A small change delta x in x produces a small change delta u in u, and that produces a small change delta y in y. Look at the algebraic identity. Delta y over delta x equals delta u over delta u times delta u over delta x. Assuming delta u is non-zero, we can multiply by delta u and divide by delta u without changing anything. Now take delta x to 0. Because g is differentiable at x, g is continuous at x, so delta u also tends to 0. The factor delta y over delta u, with delta u tending to 0, is the difference quotient for f evaluated at u, and that limit is f prime of u, which equals f prime of g of x. The factor delta u over delta x is the difference quotient for g at x, and its limit is g prime of x. Multiply the limits. The derivative of y with respect to x equals f prime of g of x times g prime of x. That's the chain rule. One honest technical note. The argument assumed delta u was non-zero. If g prime of x equals 0, you can have delta x non-zero with delta u exactly 0, and the division by delta u becomes illegal. The fix introduces an auxiliary function e of u that handles that edge case smoothly. The conclusion doesn't change, and most textbooks treat the increment-trick version as morally complete. We'll do likewise. A quick notational note that doubles as history. The chain rule in Leibniz notation reads the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x. Look at the du's. One sits in the numerator of the first fraction, the other sits in the denominator of the second. If you treat the derivative of y with respect to u and the derivative of u with respect to x as honest fractions, the du's cancel, and you're left with the derivative of y with respect to x. The chain rule reduces to algebra with fractions. This visual cancellation is not an accident. Leibniz designed his notation specifically so that the rules of calculus would look like rules of ordinary algebra applied to infinitesimal ratios. The chain rule was, for him, the most striking payoff of that design. Compare Newton's notation, which used a dot over a variable to mean a time derivative. In dot notation, the chain rule reads y dot equals the derivative of f with respect to u, times u dot t, still correct, but with no visual cancellation, no algebraic mnemonic. When 18th century textbooks started picking sides in the Newton-Leibniz priority dispute, the Continental authors went with Leibniz's notation for two reasons. He published first, and his d-fractions made the chain rule and several other rules look algebraically obvious. By 1800, even British textbooks had switched over. The notation is doing real work every time you write it. First worked example, the one we opened the episode with. Differentiate the quantity 3x plus 1 raised to the fifth. Identify the outer and inner functions. The outer is raised to the fifth, call that f of u equals u to the fifth. The inner is 3x plus 1, call that g of x. Compute both derivatives. The outer derivative, f prime of u, is 5u to the fourth by the power rule. The inner derivative, g prime of x, is 3, because the derivative of 3x plus 1 is 3. Now apply the chain rule. h prime of x equals f prime of g of x times g prime of x. Substitute. F prime of g of x means take 5u to the fourth and replace u with the inner function, 3x plus 1. That gives 5 times 3x plus 1 to the fourth. Multiply by g prime of x, which is 3. 5 times 3 is 15. The derivative is 15 times 3x plus 1 to the fourth. Done. Notice the leftover factor of 3. That's the contribution from the inner derivative. The chain rule's signature term. Forget that factor, write 5 times 3x plus 1 to the fourth, and your answer is off by a factor of 3. That's the single most common chain rule mistake. Second worked example. Differentiate sine of x squared. The outer function is sine, call it f of u equals sine u. The inner function is x squared, call it g of x equals x squared. Derivatives. F prime of u is cosine u, taking the fact that the derivative of sine is cosine on faith for now. We'll prove it next episode from the limit definition with some trigonometric setup. G prime of x is 2x by the power rule. Chain rule. Outer derivative evaluated at inner cosine of x squared times inner derivative 2x. The product is 2x times cosine of x squared, which we usually write with the polynomial factor first. Done. A quick sanity check on notation. Sine of x squared is not the same as sine squared of x. Sine of x squared means feed x squared into sine. Sine squared of x means take sine of x and then square it. Both functions need the chain rule, but with different inner and outer pairings. For sine of x squared, outer is sine, inner is x squared. For sine squared of x, outer is u squared, inner is sine x. The two functions have different graphs and different derivatives. Read your function carefully before identifying the outer. Third worked example, and it's the one that appears in every differential equation textbook for the next 3 years of your education. Differentiate e to the 3x. Outer is e to the u, the exponential. Inner is 3x. Outer derivative, e to the u, is its own derivative. Again on faith for now, we'll define e and prove this in episode 8. Inner derivative, g prime of 3x is 3. Chain rule, outer derivative of inner times inner derivative. E to the 3x times 3. The answer is 3 times e to the 3x. Notice the structure. The derivative of e to the 3x is 3 times e to the 3x. The exponential reproduces itself, and the inner derivative, 3, appears as a multiplicative factor. The pattern generalizes immediately. For any constant k, the derivative of e to the kx is k times e to the kx. This is why exponentials are the natural solutions to linear differential equations. Differentiating e to the kx just multiplies by k. Radioactive decay, capacitor discharge, population growth, every damped oscillator, and every RLC circuit, all of them ride on this one chain rule fact. Now the showpiece. Differentiate sine of cosine of x squared, a 3-level composition. Outermost is sine of something. Inside the sine sits cosine of something. Inside the cosine sits x squared, 3 levels deep, the chain rule chains. Peel from the outside in. Outermost derivative, the derivative of sine is cosine, so the first factor is cosine of whatever was inside the sine, that is, cosine of x squared. Middle derivative, the derivative of cosine is minus sine, evaluated at whatever was inside the cosine, that is, minus sine of x squared. Innermost derivative, the derivative of x squared is 2x. Multiply all 3 factors. Cosine of x squared times minus sine of x squared times 2x. Rearrange for readability, minus 2x sine of x squared, cosine of x squared. 3 levels, 3 factors, all multiplied. The rule of thumb is general. For an n-level composition, you multiply n derivative factors, each evaluated at the next inner level. The chain rule chains. This is what every neural network backprop algorithm is computing, in the end. Long chains of partial derivatives, multiplied. The same formula calculus students have been using since 1700. A quick consistency check. Last episode, the quotient rule handed us the power rule for negative integer exponents. Let's get the same result from the chain rule instead. Write x to the minus n as the quantity x to the n raised to the minus 1. Outer function u to the minus 1. Inner function x to the n. Outer derivative minus u to the minus 2. Inner derivative n times x to the n minus 1. Chain rule, plug in, minus the quantity x to the n squared in the denominator, that's x to the 2n, times nx to the n minus 1 in the numerator. Combine minus n times x to the n minus 1 divided by x to the 2n. Simplify the exponents. N minus 1 minus 2n equals minus n minus 1. Final answer, minus n times x to the minus n minus 1. Same answer as the quotient rule derivation, but without dividing by anything. The chain rule and the quotient rule agree on every common case. That's a good sanity check that we stated everything correctly. And now the payoff we've been promising for 2 episodes. The power rule for any real exponent alpha, not just positive integers, not just negative integers, but every real number. The trick is one identity plus the chain rule. Any positive x raised to the alpha can be rewritten as e to the alpha times log x. That's because e to the log x is just x, so e to the alpha log x is x to the alpha. Now differentiate. The outer function is e to the u. The inner is alpha times log x. Outer derivative, e to the u, which equals e to the alpha log x, which equals x to the alpha back. Inner derivative, alpha times the derivative of log x, which is alpha times 1 over x, taking the derivative of the natural log on faith for now. That's an episode 8 result. Multiply. X to the alpha times alpha over x. Combine exponents, x to the alpha minus 1. Multiply by alpha. The derivative of x to the alpha is alpha times x to the alpha minus 1. The full power rule for any real exponent in 3 lines. The technique has a name, logarithmic differentiation, and we'll do it more carefully in episode 8, once we've actually proved that the derivative of log x is 1 over x. For now, file the result. The power rule we've been using freely since episode 4 works for every real exponent. One pitfall, and it's the only chain rule pitfall worth flagging because it accounts for the overwhelming majority of chain rule mistakes. Forgetting the inner derivative. Each of today's 3 worked examples has a wrong version that a student writes when they remember the chain rule structure partially. For 3x plus 1 to the 5th, the wrong answer is 5 times 3x plus 1 to the 4th. They did the outer derivative, forgot the factor of 3 from the inner. For sine of x squared, the wrong answer is cosine of x squared outer done, factor of 2x dropped. For e to the 3x, the wrong answer is e to the 3x, outer done, factor of 3 forgotten. In each case, the student is treating the inner function as if it were just x, as if the inner derivative were always 1. The chain rule's whole job is to correct for the fact that the inner function is not just x. The rule of thumb that locks it in, every time you peel off a layer of composition, you owe a factor for the next layer in. Each layer, 1 factor. If your final answer doesn't carry 1 factor per layer of the original composition, you forgot one. Why this matters for everything that follows. 3 reasons. First, with the chain rule joined to the other 5 rules, every elementary function you can write down by combining powers, trig, exponentials, and logarithms through addition, multiplication, division, and composition is now differentiable in a finite number of mechanical steps. You will not need the limit definition again unless you are proving a new rule. Second, several upcoming techniques are really the chain rule in disguise. Implicit differentiation in episode 9 is a chain rule with one of the variables hidden. One substitution for integrals in the second playlist is the chain rule played backward. Both fall out of today's formula. Third, far beyond first-year calculus, the chain rule is the engine that drives nearly every applied subject that uses calculus. Lagrangian mechanics, Hamiltonian mechanics, the heat equation, the wave equation, every partial differential equation in mathematical physics. All of them rest on chain rule calculations in one or several variables. And in machine learning, the backpropagation algorithm that trains every neural network in production is the chain rule, applied recursively through layers, with each weight update computed as a product of derivatives. The same formula from 1700 runs every modern AI. Where we landed today. One new rule, the biggest of them all. The chain rule, the derivative of f composed with g at x equals f prime of g of x times g prime of x. In Leibniz notation, the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x, with the du's appearing to cancel. A feature of Leibniz's notation, not a coincidence. The cleanest physical intuition is the hiker on the mountain. Temperature changes per meter times meters per second gives temperature change per second with units that cancel exactly the way the chain rule's factors multiply. The proof is the increment trick. Delta y over delta x equals delta y over delta u times delta u over delta x. Then take the limit as delta x tends to 0, with a small technical subtlety when g prime is 0 that the auxiliary function proof handles cleanly. 4 worked examples. 3x plus 1 to the 5th gives 15 times 3x plus 1 to the 4th. Sine of x squared gives 2x cosine of x squared. E to the 3x gives 3e to the 3x. And the 3-level composition sign of cosine of x squared gives minus 2x sine of x squared cosine of x squared. One pitfall, forgetting the inner derivative, one factor per layer. And one payoff, the power rule for every real exponent, via x to the alpha equals e to the alpha log x and one chain rule, with the full proof waiting in episode 8. Next time, derivatives of the trigonometric functions, including the long-deferred proof that the derivative of sine really is cosine, from the limit definition, with the squeeze theorem and a clever bit of geometry. See you there. The chain rule multiplies 2 rates to get a third. The way this channel grows is one comment, one share, each one multiplying the reach of the last. Thanks for adding your factor. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.